case the automatic attendance fails. Okay, so welcome. Today's topic is trees. So we're going to look at what actually are trees in computer science and the terminology, how to traverse a tree, which means how to go through every node of a tree. And we're going to discuss also a special type of tree called binary trees, and at least one application of a binary tree. So after this module, you should be able to know what makes a tree a binary tree and how to traverse a tree in 3 different ways. Okay, you've actually seen trees before in just using your computer. Like in your hard disk, you may have different folders in your hard disk and then subfolders. So that's actually a tree. It's these directories and the directories within the directories and the files. The files are what we could call the leaves of the tree. Like these files here will be the leaves of the tree. Then this type of structure is called a tree, even though it looks like it's the leaves are at the bottom. So the root of the tree would be your hard disk. Then you have many leaves here, and there's a parent-child relationship between each thing. Like this is a parent. The applications is parent to tools, and tools is parent to calculate. And yes, the tree is upside down. It is the root is at the top and the leaves are at the bottom. Later on, when we learn about graphs, you'll see also that trees are a subset of graphs. Okay, the formal terminology of a tree. The starting point here is called the root, and these connections are called edges. Okay, these are edges. The things colored brown in this picture are edges. And when you have something above something like that, it is a parent, and the thing below is called a child. Each of these things is called a node, and you can have a subtree where B is the root of a subtree within A. Now, trees have a lot of things in them, so how do we systematically access all the things in the tree? This is called traversal. Okay, traversal means that we are going to go through all the nodes in a systematic way so that we do not miss anyone out. Now, note that the nodes actually are very similar to the linked list nodes. In fact, a lot of tree nodes look exactly like the type of linked list that goes both ways. Okay, so remember we did a linked list that you can go right and you can go back left. Or a tree node looks very similar to that. In fact, a tree node looks exactly like that if it's a binary tree. So one way to traverse a simple linked list from head to tail, but 3 ways to traverse a tree. We've got what we call post order and pre-order and post order, and then there's in order, but in order only makes sense for binary trees, and we'll show you why later. So pre-order means that we first process the root, and then we process all the child nodes. So if we start at A, we're going to process the root, then we process the child node. So now we're at B. We process the root, then we process the child node. So we're at E. We process the root. Well, there's no child node, so we're done. We go back to B. So it process the next child node, which is F. So we're done. There's no roots. I mean, there are no children of F. So we go back to B, and so it'll go to the next child of B, which is G. So process G, then we go back to B. We have no more children of B, so we go back to A. So A then goes to the next child of A, which is C. C has no children, so we're done. We go back to A, and we go to the next child of A, which is D. D has 2 children, so we do the first one, H. H has no children, so we go back to D. And D has another child, so we go to I. I has 1 child, goes to J. J has no children, so go back to I. I has finished all the children, so go back to D. D has finished all the children, so go back to A. A has finished all the children, so we are done. Okay, so this is what we mean by pre-order. We do the root first. That is called pre-order. Post-order says we do the root last. So we don't process A yet. We do process the children of A. So the first child of A is B. So we don't do B yet. We process the children of B. So we go to the first child of B, which is E. So we check, we don't do E yet, we do the children of E, but E have no children. So we immediately do E. Let me change the pointer to something brighter. Where's the green? How come it didn't give me how to change the pointer one? It won't let me change the pointer. That's weird. Oh well, what to do? I hope you can see the cursor well enough at the little arrow. I want to change it to the red pointer thing, but it doesn't seem to let me do that. Okay, so anyway, E has no children, so we go back to B. B still got children, so it does the next child, F. F has no children, so it just immediately processes F and goes back to B. B still got children, so we do G first. G has no children, so we do G already. We process G, we go back to B. Now, finally, we process B because we have processed all the children of B. So then, after processing B, we go back to A, but A got more children, so we do C. C has no children, so we process C immediately. Then we go back to A. A still got children, so we don't process A yet, we go to D. D got children, so we go to H. H got no children, so we process H. Then we go back to D. D still got more children, so we go to I. I got children, so we go to J. J no children, so we process J. Then we go back to I. I has no more children, so we process I. Then we go back to D. D has no more children, so we process D. Then we go back to A. A has no more children, so we process A. So you see the sequence of processing is different from pre-order. Okay, binary trees is one of the most useful type of tree, and where instead of a random number of children, every node has at most 2 children. So it can have 0 children, 1 children, or 2 children. Oh, 1 children, that's bad English grammar. 0 children, 1 child, or 2 children. If we're teaching this in Malay, it's not so bad. In Malay or Chinese, then it'll be no problem. But in English, we have to say there's plural in English. Okay, so 0 children, 1 child, or 2 children, and we are able to distinguish the left child and the right child. So this tree is different from this tree because this tree is the left child, this tree is the right child. So when you have different children, it is a different tree. Then for binary tree, there are 3 ways to traverse the tree. The pre-order means that we do the current vertex first, and then we do the left child, and then we do the right child. In order means we do the left child, then we do the current vertex, and then we go to the right child. Post order says that we do the left child, we do the right child, then we do the current vertex. So this is an application of trees in parsing arithmetic expressions. This equation, 5 times 3 plus 7 divided by 2 minus 8, will result in this tree. So if we pass, this is the pass tree, and we write the traversals like this. If it's pre-order, then we're going to do there's 3 different traversals: pre-order, in order, and post-order, and we will show you each one by one. So in order actually gives you the original equation. Let me show you. If we do in order, that means we do the left child, then we do the current node, and then we do the right child. So if we do the left child from here, we go to here. If we do the left child from here, we go to here. If we do the left child from here, we go to here. No more children, so we do 5. Just here. Then we go to the middle, which is multiply. Is here. Then we go to the right, which is 3. Is here. Now we go back to here and we've done everything. So we go to the middle, which is plus. And then we go to the right. But we don't do this yet because we got children. So we do the left, 7. So you see 7. Then we go to the middle, which is divide. Then we go to the right, which is 2. Then we finish this one, so we go back to here. We finish this one, so we go back to here, and this is the middle, so we do the minus. Then we do the right, which is has no children, so the 8 is done immediately, and then we are done. So that is parsing in order. So in order parsing of equation 3 gives us the normal way we write equations. Okay? But without the parentheses. If we do pre-order, that is essentially like making each function a function call. So if we do pre-order, we are doing the first, we are doing the middle first. Okay, so it's like making a function call on each of these as a function. So we do the minus function first. Then we go to the left child, we do the plus function. We go to the left child, we do the multiply function. We go to the left child, no children left, so 5, and then 3. Okay, 5, then 3. So we do the multiply function on 5 and 3, right? Then we return and we do the right side. We do the divide function. We do the left side, which is 7. We do the right side, which is 2. And then that's the end of the multiplication function. So we go back to the plus function to do the, we go back to the plus function. We've already done the plus function. So we go back to the minus function and we do the right side of the minus function, which is 8. So you end up with this function called minus plus multiply 5, 3 divide 7, 2, 8. This is what happens if we do a pre-order traversal of this arithmetic tree. By the way, even though we are recording this for all the other students, you can stop me and ask questions if anything is not clear, okay? So please do unmute and ask me questions if something is not clear. Then post-order, this is how the arithmetic using the reverse Polish notation calculator works. It's also how it works with a stack. Let me show you. Post-order means we do the left child, the right child, then we do the middle. So starting from minus here, we do the left child. Starting from plus here, we do the left child. Starting from multiply here, we do the left child, which is 5. So we put 5 in there. 5 in there, then that means we have 5. It's like pushing 5 onto the stack. Then we come back to the middle. The middle has nothing. So we are going to have, sorry, not the middle has nothing. The middle doesn't get done yet. We do the right child, which is 3. So now we've got 5 on the bottom of the stack. Can I draw or not? I think this doesn't let me draw. I think the problem is because I'm sharing this in a screen and not as a presentation. Let me try and do this as a presentation. Escape this. Okay, maybe I just draw it in here for now. I draw it in here like this. So I insert a text box here. So I push the 5 on the bottom of the stack. Then I go back up and I come down. I push the 3 on the bottom of the stack. 3. I mean, I push 3 onto the top of the stack, which means that the 5 goes further down now, right? Then I go back up to do the multiply. So 5 times 3. So I take the two things there and become 15. 15. So the stack, I pop the two things off the top of the stack. Remember, I had 5 and then I had 3, right? I had 5 and then I push 3. So I pop the two things off the stack and do this multiply. So that gives me 15. Then I come up to the plus. I don't do that yet because I'm doing post order. So I go to this divide. I don't do this yet because I'm doing post order. So I get the 7. So I push 7 on the stack. Then I come to the 2. I push 2 on the stack. Then I come to the divide. So I pop these 2 off and do the division. 7 divided by 2. Okay, which is 3.5. Okay, so now I'm here. I go back to the plus. So I pop these 2 off the stack and do the plus. So which means that it's 15, 16, 17, 18. So I'll get 18.5. Okay, get 18.5. Now I go back up to here. And I don't do this yet. I go to do the 8. So I push 8 on the stack. Then I come back up to the minus. And then I get 18.5 minus 8. Pop the two things off the stack. And I end up with 10.5, which is the correct answer for this equation. Okay, so that's what happens. So post order, you see, is actually using a stack to calculate your arithmetic equation, which is why those old calculators, the reverse Polish notation calculators, actually use post order because they are actually using a stack inside the calculator. So, in summary, a tree is composed of nodes that's connected by edges. So each of those round things I do last time was the nodes, and each of those lines was the edges. And the nodes have relationships. They are parent-child relationships, which is the one on top is the parent and the one below is the child. And then there are the siblings, which are the ones on the same level. And the start of the tree we call the root node. And there's a special type of tree called binary tree, where each node has 2 or fewer children. And it has an important distinction between the order. The left child and the right child is different. There seems to be an extra space there. And the way that we traverse a tree is doing it recursively by calling each other next. Have you all learned recursion already in the previous class? Can you tell me, have you learned recursion already? Anybody can tell me in your previous classes, have you learned recursion already? Not sure. So if you haven't learned recursion, then I probably need to go through a class on recursion. Okay. Let me see if I've got lecture notes ready for recursion. Recursion. Lecture notes on recursion, array and recursive list stack. Circulating the oh wait, no wonder I can't find, because I'm looking at my current lecture notes that are prepared. I should be looking at my old lecture notes from engineering days. Engineering material, lecture notes. Yeah, recursion is calling itself over and over. And that's how you can traverse a tree easily. So that's what I was referring to. So if you haven't done recursion before, then I probably should teach you recursion. But let me see where my old engineering notes still have a recursion. I'm pretty sure I have it from my own engineering notes, but my engineering notes are so many years ago, so I can't remember exactly. Yeah, I do have recursion here. Should I teach it now or let me see. Maybe I teach this next time now, because if I try and teach it now, then it'll be like I haven't prepared properly, so it could be. So I'll just go through here, but if anything, because I may refer to recursion, and it's not clear to you yet because you haven't learned it yet, then I will I will have to explain further lah. I'm also going to put a note here that if I teach this class again, I should teach recursion earlier. So let me, where is my to-do list? That's my to-do list. To-do list. So I should teach recursion before trees. Okay. Yeah, this is what happens when it's the first time I'm teaching this class to you guys and I don't know what you've learned before because I never taught diploma classes before. So sorry about that. But anyway, we'll go on for now. Then I'll try and teach recursion soon. If it's too confusing, then I'll stop and explain further. Okay, so anyway, to implement binary trees, we have 3 modules we will implement in C++ using different data structures. First one is using linked lists. Another one is using arrays with index referencing, and another one is using arrays with index calculation. So after this, you should be able to implement binary trees in C++ and write C++ functions to traverse a binary tree. So these 3 modules code will implement the same binary tree using 3 different ways of implementing, and will traverse the tree in pre-order, in order, and post-order. Okay. So first one we'll look at is linked list. Start. So we're now going to implement a binary tree using linked list and do the traversal, and our processing is just to print the contents of each node. Okay. You can change the processing as you need to. Okay, so here are the preview questions. How do we define a binary tree node? How do we create and initialize a new node? How do we link to the children? How do we build a tree? And how can I visualize the tree that we built using BP diagrams? How do we traverse the tree? And how I can visualize traversing the tree with BP diagrams? And are there other ways to implement a tree? Okay, so here is the code for a linked list linked list implementation of a binary tree. Here we're going to make this bin tree node, okay, and it has a data which is just a character, and it has a pointer to the left and a pointer to the right. So you notice this looks very much like the node for the doubly linked list, right? It's this, in fact, the structure is exactly the same as the doubly linked list. We just changed the name only. Okay, so then we have, oh, by the way, I note that in C++, when you define the record, you do need to use the word struct. But when you are declaring variables, you actually don't need to use the word struct here. You can leave out that word struct and it'll still work in C++. So you can leave out the word struct here, you can leave out the word struct here. But if you put in also, it still works. Okay, so I actually figured that out just like last week. Because like I said, I don't write C++ a lot. I write Java. And before that, I wrote C. And after that, I wrote Python and Kotlin. So I haven't been using C++ very much at all. So I just happened to notice that, oh, if you leave out the word struct, it still works in the declaration of variables and pointers. Okay, only in the declaration, not in the definition. Definition, you still need the word struct. Okay, so anyway, here we have a init bin3 node, which is exactly the same as your init LL node in the doubly linked list. And the visit is a new thing. So visit is, in our case, it's just going to print the character, but in other cases, you might do some other processing. Then pre-order, in post-order, and in order, different traversals. So in the main, we're going to make a pointer for the root and parent 1 and parent 2. And to grow the tree, we are going to initialize the root to minus, because remember, we're going to put minus there. And then we do the root left is plus, because the left is plus, and the right is 8. Then parent 1 is root left. So parent 1 is now pointing at plus. Parent 1 left is multiply, and parent 1 right is divide, as shown here. Then parent 2 is parent 1 left. So parent 2 is going to be at multiply. Parent 2 left is 5, so we put this 5. Parent 2 right is 3, so we put this 3. Then we move parent 2 to parent 1 right, which is this guy here, divide. Okay, so with parent 2 left is now 7, so this guy. Parent 2 right is 2, so with this guy. And then we've finished building the tree. Now we call the pre-order, in order, and post-order to print out the tree in the different orders. So pre-order, it's going to have minus, plus, multiply, 5, 3, go back up here, divide, 7, 2, go back up, go back up, go back up to here, 8. So this is what we got pre-order. In order, we're going to do the middle first, minus, plus, multiply, 5. Sorry, minus. In order is in the middle first. In order is the left side first, then right side. Sorry, I said the wrong thing. I was doing the post order, pre-order. So I do the left side first, come here. I do the left side first, I come here. I do the left side first, I come here. I get the 5, so they get 5. Do the middle, multiply. Do the right, 3. Finish this one. Do the middle, plus. Do the left side first, 7. Middle, divide. Right, 2. Go back up to here. Do the minus. Do the 8. And then I'm done. Post order is do the children first, then only do the root. So from here, I go to the child, I go to the child, I go to the child, no more children, I do the 5. Then I do this other child, 3, multiply. So 5, 3, multiply. Go back up here, not yet do. Go down here, not yet do. Do this one, 7. Go back up here, not yet do. Do this one, 2. Then do the divide. Then do the plus. Then come up here, not yet finish, 8. Then do the minus. So we get this line. Okay. Is it clear what we mean by pre-order and in order and post-order? You need me to explain again? Okay. So here is here are the functions for the code. Okay, visit car data, see out data. So actually my visit is just print the data with a blank. Init bin3 node is just exactly like your init LL node for the doubly linked list. So I make the temp, I make a new node for the temp. And like I said, in C++, you can actually leave out the word struct here. And then put the data in from here. Make the left null, make the right null, make the left null, and then return the pointer. Okay. Then here are the traversals. So if I am doing pre-order, I visit my current node first. Then I pre-order the left and I pre-order the right. So this is what we were saying about recursion. You notice that pre-order calls pre-order. So that is recursion. Okay. So for now, you just understand that much. Later on, I'll teach you recursion in detail. Post-order. Post-order is I do the left, I do the right, then I do my cut myself. Then in order, I do the left, I do the myself, then I do the right. Okay, so you see how it goes through in exactly what we said. The conceptual, the C++ code is actually following the conceptual very closely. Okay. Okay, so let's look at the questions again. How do we define a node for a binary tree? Well, we need the data to be stored, whatever kind of data you have in car, float, or user-defined record. Then we need a pointer to the left child, which is a pointer to the same structure. And a pointer to the right child, which is again pointed to the same structure. So here's our example node. It's like our linked list, but 2 pointers, not 1. So it's like a single, it's actually like a doubly linked list because the doubly linked list also has 2 pointers, right? How do we create and initialize a new node? It's very similar to linked lists. We have the memory allocation, the initialization of variables. So we have this function init bin3 node, and we illustrate it with a diagram. So here we have, the declaration of the function takes a character, so the data is in here. And then I make a 10 pointer. This is my 10 pointer. I make a new node, so I allocate the memory for this node. I put the data into the data of the new node. I make the left now, I make the right now, and then I return the pointer to the calling program. Okay, so this is exactly like your linked list node, except with an extra pointer, or it's in fact exactly like your doubly linked list node. Exactly. Only the names are changed. How to link to the children? We have to start from the root and initialize the parent and child node and link to the left child. The parent left goes to the child. To link to the right child, parent right goes to the child. Okay. So do we build the tree upside down? So upside down tree. So we start at the root. You work down the tree, adding children as in main. And once the child is added, it can have children. And another way is that you can build the subtree. Like I could build this one first, and then I put this one and connect it. So this is the VP diagram of the same tree. Okay, the same tree VP diagram. So the root points to here, the left goes to here, the right goes to here. The right one has now. The left one got this one and this one. This one got this one and this one. And this one got now and now. This one got now and now. So the VP diagram mirrors the structure of the tree. Okay? Is this all clear? No problems. Nobody's asking questions. I hope it's not just because you are shy, because I want you to understand how this is done, okay? So it's no point being shy and don't ask questions. If you don't understand, please ask questions. Huh? Okay, someone says it's clear. Okay, at least it's clear for this one student. I hope it's clear for the others also. So how do we traverse the tree? We use recursion, like we mentioned earlier. The base case and the else block does nothing. The recursive case, the statement order depends on the type of traversal. So the base, so if the node is now, then we do nothing. There's no else. Okay. But if the node has something, then we do, in the case of pre-order, we do myself, the left child, and the right child. In the case of post-order, we do left child, right child, myself. In the case of in-order, I do left child, myself, right child. So the statement order depends on the type of traversal. Otherwise, everything is the same. Hello, what are you doing? Oh, what happened to your hand? You got scratched, huh? Monique, go and put. Okay. Monique's the cat. Okay, so how can I visualize traversal with VP diagrams? So here we start at the root, we traverse, we go here. So we either do left child, middle, right child, for example. So if I do left child and go here, I go left child. So it's exactly the VP diagram follows exactly what we're doing. So in summary, a tree is traversed recursively using very compact functions. And the linked list style has a very flexible implementation. You just make more nodes as you need more nodes. But is that the only way to implement a tree? So there are other ways. You can use arrays to implement trees. And the advantage is that it can be compact if the data set is a specific size. If you know the size of the data ahead of time, then you can make it very compact. But the drawback is that if you don't know the size, or if you later on realize that you need to increase the size, then it causes problems. If the tree shrinks also, basically if the size keeps changing, then arrays is not so good, unless you don't mind wasting space. So now we're going to look at an array style binary tree. Okay, we're going to implement it in C++ an array style binary tree and write C++ functions to traverse an array style binary tree. Okay, we can make a tree using an array of records, and each record contains the information for one node. So my record has a data record, has a data and variable, as a left variable and a right variable. And the data variable is whatever type you want of the data, in this case, characters. And the left and the right are indices into your array. So in this case, left is 1, right is 2. So then the left child of this is node number 1, which has the plus, and it has the left child is 3 and 4. So 3 is this multiply, 5 and 6, and 5 has the value 5, and we put -1 to indicate that there is no children. Okay, so this is how we do using arrays instead of a linked list. So we're going to look at the code for implementing a binary tree using array style and traversing the tree in pre-order, in-order, and post-order, and printing the contents of each node. So how is the node defined? Okay, so these are the questions. It's very similar to the previous questions. How is the node defined? How is the tree declared and initialized? What does the tree look like if VP diagrams are used? How is the traversal done? What are the strengths and weaknesses of this approach? And why might we use this implementation? Okay, so here is the code. Here you need to have a maximum number of nodes. So this is the main limitation of the array style, because you need to know ahead of time how many nodes you want to have. And then the node record now doesn't have pointers. Instead, it has integers for the left and right, because you're going in the indices of the array. Initializing it is easier because you can just type all the data like that from our table just now. Remember from this table? From this table, you just type it all in and it initializes it immediately for you. Then, and note that this is an array of records. Okay, just like we did array of records earlier. And again, in C++, you can actually leave out the word struct here for the declaration. And for the declaration of the variable tree, the tree array variable, you can leave out the word struct. So visit, pre-order and post-order and in-order. Visit looks the same, but the actually the visit not quite the same, because we are just giving it the data, and the pre-order and post-order and in-order, they take the integer instead of a pointer. Okay, the main looks very much the same, except that instead of passing pointers, we're passing integers. The visit, we just print the data. And the pre-order now, remember last time we just checked to see if node, because if node means if node equals now, right? Sorry, if node is not equals now. Well, here we cannot say if node because 0 is actually a node, right? So it's actually say if node not equals -1 because we're using -1 to mean that there is no data. It's no leaf there. So if node is not equals to -1, then we'll do the visits. If node is -1, then we know that there is no leaf there, so we stop. So visit tree node dot data instead of the pointer arrow data is now 3 square bracket node dot data because it's an array. And the pre-order 3 node left, pre-order 3 node right. So it's very similar except that the pointers are all gone. So for the in order and post order, we do exactly the same thing. Okay. Oh, somebody just sent me a message. Miss Yu Yan, sorry, can't attend your class today because my house is doing renovations during the Okay, then just watch the recording later after I post it on what's it called already? Edpuzzle. Those people who are watching this by recording, please make sure you watch it on Edpuzzle and not directly, because otherwise it won't take your attendance. If you watch directly, it doesn't take your attendance for watching. So if you're watching this directly and not through Edpuzzle, stop and go to the Edpuzzle so that it'll take your attendance. But those who are watching live, no problem. Your attendance is being recorded. You already typed in the chat box, and hopefully the automatic attendance system will work properly and it will be fine. So anyway, to do the same functions for in order and post order, you just make the same modification. Turn all those pointers into indices into the tree, into the array. Okay. So the output looks exactly the same because after all, this is a data structure and we are telling you what it should do. We're not telling you how to implement. So when you use it the way it should do, then you get the same result. Whether or not I'm implementing it with linked list or whether I'm implementing with array, you get the same result. Only thing is that maybe the speed is slightly different. Okay, so output is the same as the bin tree version. Oh, I forgot to change this to C++. Yeah, this, as you can tell, I modified this from my original engineering lecture slides, which were all done in C and not C++. So I've been translating everything to C++ for you. Okay, so let's look at the questions. How is a node defined? How is a tree declared and initialized? What does the tree look like if a VP diagram are used? And how is the traversal done? And what are the strengths and weaknesses of this approach? And why might we use this implementation? So the node is defined like this. You see the difference? The original linked list node has a pointer here and a pointer here. This one has just left and right. Okay, so and of course, like I said, you can leave out the word struct here. You cannot leave out the word struct here, but you can leave out the word struct here. And this is how you define the node. And the main difference is that all those pointers became integers now. How is the tree declared and initialized? We can declare the whole tree in one array. So, or you can initialize one at a time, or you can initialize it later, like in the linked list. But the advantage here is that you can declare the whole tree one shot. And what does the tree look like if VP diagrams are used? Because it's an array of records, so it's contiguous memory locations. So each item in the array is a record, and each record has that structure of the record. So each node occupies 3 memory blocks. And the traversal is done with the root node at 0, and then you visit the tree data, and you recurse 0's left child, visit node 1, you get a plus, recurse 1's left child, node 3, visit, and you get this multiply, recurse 3's left child, node 5, visit, and you get 5, and recurse 5 left child, -1, so we return immediately without doing anything. Right child -1, return immediately without doing anything. And we continue on with 3's right child and all that. Okay, so it's quite straightforward, just like the pointer version. So the strengths of the array-based version is that it's easier to initialize the tree and your code is shorter. But the weakness is that the size is fixed. You have to reallocate the memory if the size of the data set changes. Actually, it's realloc is the C version. I'm not sure what it is in C++. I forgot to look it up. Maybe I'll try and look it up now and see. Let me see how to realloc in C++. The realloc function is only used for those you make using malloc and calloc. So you can't use it with those using new. So it doesn't answer the question. But anyway, oh, maybe this Stack Overflow might say. There's new and delete, and then and they're saying to use vector and stuff like that. So there isn't a straightforward way in C++. But you are allowed to use the C way of using malloc and realloc. Okay, now why would we use this implementation? Well, there are languages that don't have pointers, so you might use this implementation. But even with languages with pointers, there's the ease of initialization and easy to change node data if tree structure is static. So a binary tree can be implemented using an array of records as a data structure. And each record or node contains the data, the array index of the left child, array index of the right child, and it's useful for immutable data, which means the data doesn't change. Okay, so it makes it very fast when you're doing immutable data. Okay, so now it's 10:48. Let's take a break until 11. We'll come back at 11. Okay. So I guess I should put on my should put a Firefox up and say we come back at 11. So 11 is 10 minutes, 11 minutes away. Or now it's 10 minutes away. Okay. So, well, actually, it's a bit more than. Okay, I'll just say 11 minutes away. Okay, so we'll come back in a little while. Okay, so we continue. But there's another way to do binary trees using array index calculation. So we're going to look at UNCC. I thought I changed all the UNCC. Did I not? Did I forget to change this part? Index calculation. Did my code change? Binary calculation. Actually, I did update the code to C++. Apparently, I didn't change the word UNCC here. I did update the code to C++. C++. C++, and at the CPP already. As you can see, the code actually I've already updated the CPP. I just forgot to change the title here. Okay, so for array index calculation, we will implement this binary tree using index calculation. So we'll see how you actually do this. Binary tree using index calculation, doing the pre-order, in-order, and post-order traversal again, and printing the contents of each node. Now, the key to this method is that the index is figured out by calculation and not by actually storing the index. So the index of the left child is the index of the parents times 2. And the index of the right child is the index of the parents times 2 plus 1. So the blank node in position 0, we cannot use. Okay, position 0 we cannot use because if it's 0 times 2 is still 0. So you can't find the child. Okay, so we start from position 1. So what are the key differences between this and the previous base array implementation? How do we specify an empty node? How do we check to see if a tested node is valid? And how can we visualize what's happening in the program? And why will we use this method? Okay, here now, instead of defining the number of nodes, we define the maximum depth of the node. And the array size is maximum depth times maximum depth. So it's maximum depth squared. So 0 is nothing. So we just put a null there. And then the node we actually use, the first node is the root. The second node is the 2 children of the root. Then you've got the 4 children of the next level and the 8 children of the next level. And I purposely typed it in like this so you can see the tree visually. And visit is just the data, and then valid is whether the node is valid, and left child, right child, pre-order, post-order, in order. Okay, so left child calculates the left child of this guy, right child calculates the right child of this guy. So instead of the left child and right child being stored in the record, it's actually calculated. So that's why left child and right child are functions rather than pointers or some storage. So the pre-order traversal of the root to the root is 1. Okay, so the root is 1, so it passes in 1. And then the visit is just cout data like last time. And we check to see if it's valid by checking this. First of all, is the node number too big or not? If it's not too big, then we check to see is the node there got valid value or not. Okay, because you see what we did was we put null characters where there's no valid value. Okay, so where the tree is not there, we actually put null characters instead of an actual character. So when we check to see if it's valid, then the left child returns the root times 2, the right child returns root times 2 plus 1. So in order, pre-order, we say if valid node. Okay, so valid, because this valid is not a trivial test, we actually wrote a function for it, which is we check to see if the node is less than, the node number is less than max depth squared, and the tree at the node is not, and the tree at the node is a valid character, basically. So then we pre-order node times 2, post-order node times 2. So this is actually left child, right child, see? Here we wrote it out to show you, but here we're actually calling the left child and right child. So if you really did it properly, you would just call left child and right child here, but we wrote it out so they can see what is actually left child and right child doing. So post order, left child, right child, visit. In order, we do the left child, visit, then right child. Okay. So the result printout is exactly the same as before, because after all, it's the same tree, even though it's stored in a different way. So yeah, the not C, but C++. I forgot to change that to C++. C++. So actually, this code, this could well be have said left child and right child, just like that. Oops, undo. This code could have just said left child and right child, the same as that. Okay. So what are the key differences between this and the previous array-based implementation? How do we specify an empty node? How do we check to see if the tested node is valid? And how do we visualize what's happening in the program? And why would we use this method? Now, the big difference between this and the previous array method is that we do not store any indices, and also, unlike the linked list method, we do not store any pointers. Instead, to figure out the left child and right child, we calculate it. So initialization is laid out in a nice tree fashion, like I showed you in this slide here. In this slide, see the initialization is laid out in a nice tree fashion. And if the tree is not full, there is wasted space. So that the tree we showed you just now was not full. So 6 nodes used, the rest of it is wasted in this particular example. So how do we specify an empty node? If the tree is not full, we have empty nodes. We store a special value which will never occur. For example, using the null character, since this won't occur in the data because our data is character data. So depending on what kind of data you have, you need to choose a value for the invalid data notification. On invalid data for indicating invalid data. Okay. So how do we check to see if a tested node is valid? We have to see 2 things. One is the index out of the array? If it's out of the array, it's not valid. Or if the data is the special value of null. In this case, we oh, sorry, when I came back, it was muted. Okay, how much of the lecture did you lose? Was I already on this page before I lost connection? Can someone tell me, do I need to back up to the previous page? Hello? Can anyone tell me when did I lose connection? Because I only noticed it when I was on this page. Was I already on this page when I lost connection? Is anyone there? Hello? Yes, okay. Yes, meaning I was already on this page. Okay, so I'll just start from this page. Okay, all right. Okay, so to check to see if a node is valid, we've got two things to check. One is this is the node out of the array. If the node was out of this array, then definitely it's not valid. The other thing is to check to see if the data is valid. So for this case, we were using characters, so we use the null character as an invalid data. So if we have a null character, then it is not valid. So either case, we return 0. That's why we do this and this. We return this and this. If this is true, then this is if this is true, node less than depth, then it is valid. If node is if tree node has a value that is valid, then it's valid. This both have to be valid. Okay, and note that we put this here because in C++ we have this short circuiting sort of and when if this is false already, it doesn't bother to check this. And this is very important because you cannot check this if this is false already. Okay. So it works in C++ because of this short circuiting AND. It checks this one. If this one's false, it doesn't bother to check this one. Okay. So if you are using a data set that is not characters, then you have to make a different sort of special value for the invalid. What will it be returned when both are true? Is it return 1? Yes, it's return 1 if both are true. It's good to unmute and ask your question because I may not see the chat box. Okay, but fortunately I happen to see the chat box this time. So your question, what will it return when both are true, is it will return 1. So if the node is within the array and the value is valid, then it will return 1, which is true. And the if that you use here, this if will return true, so you will do this part. So, okay. All right, so how can we visualize what is happening in the program? So actually, if we are at node slash divide this node, that means we're at position 5. The left child is 5 times 2, which is 10. So it's the one that has 7 here, position 10. The right child is 5 times 2 plus 1, which is 11. So it's the 2. So we've got the 7 and the 2 here. See? The parent is 5 divided by 2, which is this plus here. So you can navigate this whole thing, this whole tree very quickly, and by just using this calculation. Okay. The thing is that you will waste space if your tree is not full. Why would we use this method? If you have a full tree, there is no space wasted and no need for pointers because you're calculating all the indices. And in fact, note that we are only multiplying by 2 or dividing by 2. And multiplying and dividing by 2, when you compile it, it actually optimizes to machine calculation, shift left and shift right. Okay, so divide by 2 is and multiply by 2 is turned into machine instruction, shift left and shift right, which are very fast, efficient machine instructions. And increment is also a very fast machine instruction. So these machine instructions are very fast in the processor. And so if you're doing a lookup of a huge tree, like a tree with, like, you could have a 10 gigabyte tree. If it's full, then finding your actual place is very, very fast. Very fast to find your place in the tree, and faster than doing the pointer or the normal arrays. So for example, in using heap sort, which we will discuss later, it will show this, it can use this kind of tree to make it very fast. So shift left is a one cycle operation implemented on all ordinary microprocessors. It shifts the bits of the binary number left. So for example, 5 is 000000101. Shifting left would give us all these bits to shift left by 1. So there's an extra 0 here. So it's 10. See, because this is 1 plus 0 plus 4. So 1, 2, 4. So 4 plus 1 is 5. Whereas this is 2, 4, 8. 8 plus 4 is 2. So 1, 2, 4, 8. Yeah, 8 plus 2 is 10. Okay. So doing this kind of operations is very fast in the processor. Shift right is also a one cycle operation. You just shift the bits right. So 5, shift right, you get 2. See? This is 5. You shift right, this is 2. Okay. So this makes it very, very efficient. Shift left and increment will take 2 machine cycles. It's still very fast. So this one, shift left, you get 10. And then add 1, which is 11. Also very fast. So binary trees by index calculation makes it for very efficient speed. And if your tree is nearly full, also very efficient memory allocation. So using this kind of binary tree is useful when your trees are full and it doesn't grow or shrink. Okay, the size stays the same. Then this is a very useful type of tree. It makes it fast. So in summary, we have seen how to traverse general trees recursively using very compact functions, and we have implemented binary trees. And a variety of data structures can be used to implement binary trees. We saw linked lists, which is the most natural. Okay, you have links for everything. But the other types of link, the array-based ones also have some reasons for using it depending on the situation. And we can find everything by following the traversal of the trees. So choosing a tree implementation. The food is here. Someone go and get it. I'm teaching the class, so I can't go. Lunch delivery. Okay. Yeah, we've been trying to avoid going out to buy stuff, so we have been doing a lot of delivery. I don't know about you guys. And fortunately for us, our Chap Fund, our economy rice shop in the village near my house, Batu Ampabas Puchong village, he actually will deliver. He started doing it more than a year ago at the start of the pandemic. He told me, I can deliver. So great. Then so we've been getting deliveries from him when we're too busy to cook and stuff like that. So anyway, choosing a tree implementation. So if you want full flexibility in the tree structure in insertion and deletion, and you don't mind using more memory and things take a bit longer, then you should use linked list implementation, because the linked list implementation lets you add and remove nodes easily. Because it's linked list, you can put things anywhere, you can find things, but of course you have to follow the links, so it's a bit slower. But if you're using a language without pointers, or if the tree is static and sparse, and you want to make it easy for initialization, and you don't mind that the tree size is limited by the array size, then you could do array by index referencing. Okay, That was the second method we did. If you want to have very fast access of the nodes is in initialization, and you have the tree size limited by array size, you don't mind having the tree size limited by array size and having a static structure. And if your tree is sparse like array space, then you can do array by index calculation. Okay. So we have been mainly discussing binary trees, because binary trees are actually the most useful in most applications in computer science programming. But there's also others. There's array by index calculation. Okay. Array by index calculation. I'm sorry, I got distracted by the. Okay, so we've been doing binary trees mainly, but there's also other types of trees. Okay, there are other types of trees. We mentioned them earlier. So you can move from a single character into complex storage, because earlier we saw single character trees. Okay. Sorry, this is still binary trees. This is generalizing binary tree nodes. Sorry, I got distracted by the term generalizing. So what I said for the last 1 minute is wrong, because we're not going to generalize generalized trees right now. We're doing generalizing binary tree nodes, meaning that if you want to store more things, than just character, you can just put more things in the record. Okay, so you can have a student name, you can have a student ID, you can have a mark, letter grade. So if this is a data to store, you could put the record in there, for example. Okay. So okay. Now I'm going to look at this is the end of the tree. This is the end of the tree lecture. Now we're going back to the application question from last time. And something is wrong with my screen because I'm seeing this in mirror and I don't want to see it in mirror. Yeah, it's still showing it in mirror. Let me try something. I'm going to leave for a minute. You don't leave. I'm just going to leave for a minute. Closing.
Sir, are you muted?
Oh, I'm sorry. I guess when I left and came back, it was muted. Sorry about that. I was trying to fix the bug by leaving and coming back, but I came back and the bug is still there, so I just had to live with the bug. What you're seeing is the code is the right way, right? But on my screen, the code is the balik. So I'm seeing the mirror image, so it's going to make it a bit more difficult for me to discuss, but it's okay. I think I can manage. Okay, so this is the last lesson's application question. Okay. So I'm going to discuss it so that make sure that everybody is clear about how to do it because some teams messed up on it. Okay, so first thing is that as noted earlier, C++ allows you to leave out the word struct when declaring. So you can actually get rid of all these words struct, okay? And it'll still work correctly. But you cannot get rid of the declaration struct. Okay, you can, oh, I left out this one. You can get rid of this one also. But in the definition, you can leave out the declaration struct. You cannot leave out the definition struct. So the definition of node, most of you got it correct. You have to have this struct here. You don't have to have this here, but you can have it also. It's okay. But this is the node. You've got your name, which is your data, and then you've got the left pointer and the right pointer. So remember, this was our doubly linked list. So it looks incredibly like the tree node, right? The binary tree node looks just like this thing here. And you can have the struct there or don't have the struct there, but you have to keep this struct here. Okay, the surprising thing is that there were some teams that actually got this part wrong. They went and wrote an English definition of node, which is, I already showed you, the definition of node goes here, which means it must be code. So you cannot write English. So surprisingly, there were some teams that lost the mark here, which I thought was a free mark because it's like all of you knew how to do the node already. Okay, then new node also is free marks lah. It's pretty much the same as the new node of the normal linked list, only that you have left and right rather than just next. Some of you name it next and previous. That's fine. That's okay also, right? So although is it okay also given? See, the thing is that this is mirror image, so I can't. Oh yeah, no. So it's not okay because the main actually uses right and left. But in general, if you're writing everything from scratch, you could use left and previous and next also if you wanted to. But because the main uses right and left, I think that's right and left, right? Yeah. Current arrow right. Okay, and current arrow left. So yeah, you have to use right and left here because the main uses right and left. But if you're writing things from scratch, you could call it next and previous. It's fine. It's up to you when you're writing your program from scratch. Okay, now this is the part that most teams got at least partially wrong. Actually, a lot of teams got it almost all correct. They just forgot one thing. But firstly, this was the first picture that I showed you. So it means that we are going to pass in a name. And we have our current pointing at some linked list, right? So we have this code for this picture. Then the next picture says we're going to make a new node. So you should just use the new node that I told you to write in question 2. I don't know why a lot of people didn't use the new node they wrote in question 2, but okay, never mind. I didn't deduct marks for that. But by right, you should just use the new node you wrote in question 2. So call new node, right? So the temp pointing to the new node and the name goes into the new node. Then this picture actually doesn't have new code because actually I was just rearranging this so that you can see that it's going to fit in between here and there. But we haven't actually added any code yet. So this is the same code. Okay, now this picture says I'm going to connect the new nodes left to the current and the new nodes right to the current arrow right, because current arrow right is here, right? So I want to connect this guy to here. So that's temp right equals current arrow right. Temp right equals current arrow right. This is the crucial part. Anybody confused? I don't mind asking again, explaining again. Anybody need clarification? This is current. So this is current arrow right. It's pointing at the node containing C. This is temp. Temp arrow right. We want it to point at the node containing C. That's why we say temp arrow right equals current arrow right. Okay, temp arrow right is this pointer equals current arrow right is this pointer. So this pointer is pointing at C. So now this pointer also pointing at C. Okay. Yeah. And then I want to point this pointer back at the current. So this pointer is temp arrow left. So pointing at current. Current is pointing here. So this is pointing at B also now. Or actually pointing at the node containing B. Okay, this is the node containing C, this is the node containing B. So this is a node containing new, which is our new node, is pointed to by temp. So that's how we get these two code, these two lines of code. Okay. Then we need to point this at the new node. So current arrow right equals temp gets the new node. And this is the line that most teams missed out on. They forgot they need to get C to point back at temp, point back at the new node. So they leave out this thing. So what happens is that C remains pointing back at current. And so when you go left from C, you end up at temp. You don't end up at current, which is wrong. Okay? So many teams forgot this part and lost 1 mark. But still A lah. You lose 1 mark, you still get A. Because 4 out of 5 is still A, right? Okay. So very important that you see all the wires that need to be connected and you write the code for those wires. Okay. That's why it's very important, first of all, to draw the picture properly. And secondly, to follow all the drawings that you did. So many people left out this line. So many. Okay. I think only one team remembered to do this line, if I'm not mistaken. If I remember correctly, only one team remembered to do this line. Okay, so that looks great for if I'm inserting into a list that contains stuff already. But what if we have this situation? What if current is the rightmost item in the list already? That means there's no node C. That means current is pointing. So after doing this and this, then you end up with this current point here, and this is going to null, right? But if you say temp arrow right, arrow left equals temp, your program crashes with a segmentation fault because you that's interesting. Said you die, I lost network for a while there. So the network died. Ayo. Okay, anyway. So you cannot do this if it's null. So you must have an if. If my temp arrow right is not null, then I can do this. If it's null, I don't do this. Okay? If it's null, I don't do this. You have to check for those edge cases, those special cases of when things are not quite what you expect. Okay? So that's the end of the discussion of L4 application. It's also the end of today's lecture. Any questions before we go? If not, if you haven't typed, can I explain a bit about null part? Okay. Okay. Explain a bit about null part. Okay. You understood why I have to do this line or not? Do you understand why I had to do this line? Temp arrow right, arrow left equals temp. Was you don't really understand. Okay. If I didn't do this, if I didn't do this, then this arrow, remember this arrow was pointing at B, right? You remember? This arrow was already pointing at B. Correct? You understand that part? Yes, okay. So if it's already pointing at B, if I didn't do this part, if I didn't do this line, it would still be pointing at B, right? Right, huh? Okay. So it's not supposed to be pointing at B anymore, right? It's supposed to be pointing at new, right? Yeah? It's supposed to be pointing at new. So I need to get it to point at new. That's what this line is for. Temp arrow right, arrow left, which is this pointer here, is pointing now to temp. You understand? Yeah? Okay, now you understand that part. Now, but the problem is, it's not always that current is not the last thing, right? Sometimes current is the last thing. If it was S A and B, there was no C, then current is the last thing, right? So then temp arrow right would be pointing at null, right? You understand? So if it's pointing at null, if I go temp arrow right, I'll be at null. I can't go arrow left already. There's nothing there to go arrow left to. You see? And that's why you get segmentation fault. Segmentation fault means that you are trying to access memory that you cannot access. And it crashes your program. Okay? So now you understand the problem that it's faced here. Yeah, it's null to the right. It's because it's null to the right. Okay, so because of this problem, we need to have an if temp arrow right, which means if temp arrow right is not null, right? If temp arrow right is not null, then only we do this line. If it's null, we don't do this line. Okay? Okay. Yongping Jin, I don't remember if I released the mark already yet. If I haven't, I'll go and release it afterwards. Okay, any other questions? Okay, then happy Merdeka.